Okay, good morning. So, first of all, let's do a couple of administrative stuff. I do remind you one more time that we're going to have yes, it is that coin flip time of the week. That's correct. But before we go with the coin flip, I want to remind you about test on Wednesday. Put it on your calendar. It is at 6:30. You're going to have an hour. So from 6:30 till 7:30. I know my UI says it's from 6:30 to 8, but I decided the test is going to be a bit shorter so that everybody can go home at a normal time. We're going to discuss everything as far as what's going to be on the test. We're going to discuss it on Monday because everything we covered today and on Monday is still going to be on the test. Everything we're going to be talking about on Wednesday is going to be review. So of course, it's also going to be on the test, but it is going to be no new material on Wednesday. So you are going to have the discussion section on Wednesday. And again, this discussion session of Wednesday is going to be a review type of a discussion. So I'm still thinking if I should just give you some set of problems to do during discussion section, kind of to practice, or if you would prefer, I don't know, to just have time to ask your TAs questions. What do you think is going to be more beneficial during those 50 minutes? Would you prefer to have a worksheet, which is going to be cumulative over everything, or would you prefer to ask questions? Okay, so I see the majority has a worksheet, but some also have questions. So I think maybe it's going to be a good thing to have kind of both. So during my review section, you're going to get a chance to ask questions. And then during the discussion, you're going to have a worksheet. However, if some of you would prefer just to ask questions and ask TA to work on some problems, then the TAs are going to be happy to help you out. Okay. Now, and then at night, we are going to have our evening test, and hopefully it's going to go well. Again, it's going to be similar type of questions we did for the discussion assignments, for homework assignments, for quizzes. I don't know what we are going to get today. We are going to flip a coin in a second. However, a reminder, if it's a homework, don't forget to submit it before 10:30, so you pretty much, it's due the class. So don't forget to submit it. You will have like 10 minutes after the class to submit it too, but hopefully you already have it already in case it's a homework. If it is a quiz, triple check that you submitted everything, that there is nothing missing and everything looks good after you push the submission button. If it doesn't look good, then make sure to email me directly in the next like 5 minutes after you completed the quiz with the correct information, saying something went wrong, this was the answer I was putting in and it didn't, for example, work or something like that. Okay, but again, like plus 5 minutes, that's what you got. Okay, it doesn't have to be from the same computer. If like something went wrong with your computer, you can text from, well, hopefully send it from the cell phone if you have a cell phone which has an ability to send emails. Okay, so make sure to contact me directly. Another way is going to be just worst comes to worst, Slack me if you do not have access to email. Okay. So quiz or homework? Yes, that's a big question. I see it already in the chat multiple times. We didn't flip yet. So here we go. Let's flip. Okay, so homework it is. Don't forget to submit it. So here is what we are going to do. I'm going to release still the quiz, but it's now not going to be for credit. And your quiz is going to be like a practice quiz. So it's going to cost 0 points, but you're going to be able to try and do it. You're also going to be able to see the correct answers after you're done with the quiz. So it's kind of literally like a, you know, practice pretty much before the test. Okay, on that note, let's open up. Okay, so it is homework. You are submitting it. Don't forget to do it in a timely manner. We are going to grade it. We are also grading the discussion. And back to our material. Okay, so here we go. What we were studying is, so chapter 2 combines in itself multiple topics which maybe on the first sight seem disconnected, but they're really connected. So we started by talking about sets, and then we went to talk about functions. And if you think about it, without understanding what a set is, you also cannot understand what a function is, because the function, it moves elements from one set to another, correct? So it kind of gives you a mapping from a set to a set. So sets are needed background in order to understand how functions work. Now, functions don't always have to be continuous. There are lots of discontinuous functions, and it's actually depend on what type of set you have as your domain. We also talked about properties of functions, which are like one-to-one and onto and bijection, and you need to know how to prove those things too. This is what you did in the last discussion section. So after that, we started talking about sequences. Now, to some extent, if you think about it, sequences do look like functions, but those functions are not really continuous functions, correct? They tell you how to map integers like 1, 2, 3, 4, and so on, counting integers, into other values. And generally, those are also integer values. So this is how we get sequences. So to some extent, you can think about sequences as functions too, correct? So in order to understand sequences, you kind of need to understand functions. So there is a connection between all of those topics. They kind of give us a description of different ways you can do things, how you can use sets to create functions, and how you can use functions and how it connects to sequences and so on. So today we are going to continue talking about sequences, and we're going to start by reviewing what we did already. So we said we can represent sequence in two different ways. One way is iterative way. This means you have a formula, and it's kind of like a function, f of n equal to something. And this something has n in it, and you plug value instead of n, and you get a value. Now, the other way of representing sequence was a recurrence relation. A recurrence relation has to have two things. First thing is you need to have a formula which is going to be using previous terms. It can be one term or multiple terms, but it always uses previous term. If you look at the example on the board, you can see that we have a Fibonacci sequence, and in Fibonacci sequence, you have Fn equal to Fn minus 1 plus Fn minus 2. So it uses two previous terms and it adds it together to get the next term. So there is a recursion out here. You can repeat it as many times as you want and generate as many elements as you want. Another thing you need for recurrence relation is you need initial condition. So you need to know how to start. So today we are going to talk about going from one form of formula to another. Okay. So here we go. So assume I have a formula, an is equal to an minus 1 plus 2. First of all, is this one iterative or recursive? Yes, so it is a recurrence relation, recursive formula, and we need an initial condition. My initial condition is going to be A0 equal to 3. Oops. This is how I start. Remember how last time we talked that sometimes it's useful to have a recurrence relation, but sometimes it's, depending on what we need, it's better to have iterative formula of it. So the question is, if I know the recursive formula, can I somehow get it iterative formula of the same, recurrence relation? And the fact is, sometimes you can. Not always, but for some recursions, you can do it. And one of the ways to do it is to try and examine what's going on. So if what we're going to do is we're actually going to plug in and try to find A1, A2, and 3, and so on, but we're not going to just calculate the value. We're actually going to write down exactly what we're doing, what we're plugging in. So what we have here is we have here 3, and then we do +2, correct? That's what we do. Now let's look about A2. In A2, I suppose to take an minus 1, which is 3 plus 2, correct? Plus another 2. Agreed? Because an minus 1 is 3 plus 2. Now, please notice that I do not calculate that it's 5, and I do not try to plug in 5. And there is a reason for it. I'm trying to learn what is the pattern here. So now we are going to write the A3. A3 needs to take everything from the top, which is 3 plus 2 plus 2, and add extra 2 to it, correct? Now let's see if I have a pattern. So I kind of have 3 everywhere, correct? And I see 3 exactly once. I also add 2. The first time, how many 2's do I add? Just 1. Okay, what about the second time? How many 2's do I need to add? What about the next time? Do we see the pattern? So now we can say that my an will have a form of 3 plus 2 multiply n. And now it's a good idea to try and check, are we right? So let's plug in 1. If we plug in 1, we get 3 plus 2, which is 5, and that's correct, right? If we plug in 3, we're going to get 3 plus 6, which is 9, and guess what? It is what we got for A plus 3. So you can check yourself by writing down the actual sequence using the recursive formula. So we can say we get 3, and then 5, and then 7, and then 9, and keep on going. And then you can check it by plugging in a couple of things. Now, remember, in this case, we started, oops, come on, up, with indexing 0, 1, 2, 3, and so on. Okay, so sometimes, and we are actually going to have the whole chapter on it much later when we're going to prove those things and the more details and everything. But if somebody asks you to show an equal to negative 4n, is the solution for an equal to negative 3 an minus 1 plus 4 an minus 2. So in here, what we're trying to say by this thing is solving the recursive relation, it means that they kind of going to give the same values, but there is a thing, you need to start correctly in order to do it. So if you think about it, we already discussed it, but recursive formula is always going to depend on starting condition. And I can put any condition I want, correct? So I can say A0 is 0 and A2 is 2 and so on. What I have here is more of a general solution. And I'm saying negative 4 to the power n is one of the options of when the recursive, like there are conditions in which you can start and you can get negative 4 to the n. Now, in order to show it, what you're going to do is you're going to say, okay, assume an equal to negative 4n is, well, actually, you know what? We're not even going to assume anything. We're just going to do calculation. So, because what you kind of do is you use the formula. So let's try and use A of n. Okay, let's use an. So what we're going to do is we're going to say, okay, an is this formula out here, correct? But if it is a solution, what has to happen is I should be able to replace an minus 1 with a solution. So using this formula, an minus 1 should be negative 4 to the power n minus 1. Do you agree? We just plug it in. And an minus 2 is going to be negative 4 to the power n minus 2, correct? So what I can do is I can try and plug it in and see if it really works, to see if it is going to give me an back. So we are going to get negative 3, negative 4, n minus 1, plus 4, negative 4, n minus 2. Up. So now let's actually try and play with the numbers. So first of all, what I can do is I can say this is the same as negative 3 multiply negative 4 to the power negative 1 minus negative 4 multiply negative 4 and minus 2. Do you agree with that? So what happened here? I took plus 4 and I said, well, plus 4 is the same as minus minus 4, correct? So minus minus killing each other will give me plus, so I can do it. Now I have negative 4 here and here. So what we really have is we have negative 3 minus 4 and minus 1 minus, and then I have the same base, correct? It's like a to the power 1 multiply a to the power n minus 2. So it's the same as a to the power, well, in my case, a is negative 4 to the power n minus 2 plus 1, which is the same as negative 3 minus 4 and minus, sorry, why did I write minus 2 here? Minus 1, minus 1, because it was minus 1 before, and guess what? N minus 2 plus 1 is also n minus 1. Now you can think about it. Negative 4 to the power n minus 1 is variable x. Okay? So what I have is I have minus 3x minus x, correct? So what I can do is I can factor the x out. So I can factor the negative 4 and minus 1 out. And I'm going to have negative 3 and negative 1 left. So what we really have here is we have negative 4 to the power n minus 1 multiply n minus 4. Now, again, I have the same base, so I can do the same trick of saying what this is negative 4 to the power n minus 1 plus 1, which is the same as negative 4 to the power n. And actually, negative 4 to the power n is an. So we proved it works. We were able to go back to an. So by plugging it in and getting back an, we showed it is going to solve it. You can play with it and try to figure out what starting condition you need in order to actually get negative 4 to the power n, what sequence you need and what is going to be your starting an minus 1 and an minus 2. So what are going to be your a0 and a1, for example? This is a good exercise for you to try. Okay, great. So the next thing we need to talk about is we need to talk about summations. Summations are important things. Summation, what is a sum? It means I take some elements and I add them together, correct? This is what summation is. Now, if you think about it, if those numbers somehow connected, yes, or have some type of a formula associated with it, you really have a sequence, correct? And what you do is you're trying to add elements of this sequence together. So this is how summations are really connected. So first of all, we are going to learn notation. So the summation is like this large letter over here. So this is summation. Now, generally, summation sign has a lower limit, which you put over here, and upper limit. And generally, in here, you're going to have some type of a variable. So in here, you have some type of a variable. So here is an example. We're going to say that A1 plus A2 up to AN. What is that? Well, I'm adding things together, correct? I add A1 with A2, with A3, with A4 until I reach AN. Now let's represent it as a summation. So we need a big sign. In here, we will need to put a changing variable. So in here, we're actually going to have AI. And I is going to be our index, correct? So what we will need to do is we need to add 1, 2, 3, 4, correct? A1, A2, A3, A4, and so on. And this is where lower limit and upper limit come into place. I need to say for what i's it is going to work. So in this case, my I has to start with 1. This is my lower limit, correct? And then we are going to increment it. We are going to do I is equal to 1 and 2 and 3 and 4 and 5 until I reach what? What is my last one? N, correct. So on top, we're going to put an upper level, which is an N. So again, this is just a notation. And now we are going to play with those notations. So first, we want to know what is a summation J from 2 to 4 J plus 1 square. So how do we unscramble something like this? How do we understand what we got? So first of all, my J is going to be going from 2 to 4. It's always integers. And I'm going to say J will have to be 2 and 3 and 4, correct? So I'm going to have 3 terms. What I can do is I can substitute each of those J's into my formula and add elements together. So when J is equal to, I'm going to get 2 plus 1 square plus. Then I need to add the next element. The next element is going to be when J is equal to 3. So now instead of J, I'm going to be substituting 3. So we're going to have 3 plus 1 square. Finally, the last but not least is where we plug in 4 for J and get that. Now I can definitely calculate something like that. So we have 3 square plus 4 square plus 5 square, which is 50. So what I did now is I actually evaluated this expression, this summation, yes? Now it's your turn. So my summation is going to go from k equal to 1 to 3 and negative 2k. So how many terms am I going to get? So how many times will I need to substitute something for k? 3 is correct. Now, the first one I'm going to plug in inside of k, instead of k, is going to be value 1, correct? Again, remember, you add all the terms together. So now you're going to add negative 2 to the power and then negative 2 to the power beautiful. Now, remember, one of the interesting things about iteration and one of the things all students are too lazy to do and they pay for it with the wrong mistakes on the test is you must have the parentheses. Please, please, please don't ignore them. Please don't just put minus and so on, because this is going to get everything wrong. And the easy problem is going to become a messy problem which got you wrong answer and a mistake. So parentheses, every time you need them, put them in. So in this case, I have parentheses around negative 2 to the power k. And that means first I take negative 2 to the power 1, which is going to be negative 2. But then I take negative 2 to the power 2, which is negative 2 multiply negative 2. So I'm actually getting a positive 4. And this is important. It's not negative. And then we are going to get negative 8. So now you can see what the answer we get is -6. Now, this is very different, very, very, very different from that. It looks like it's not, but it really is. In this case, K only belongs to 2. It does not belong to minus. It doesn't have the minus inside. So actually what you have here is -2 to the power of 1 plus -1 and 2 to the power 2. So in this case, this minus is kind of converting all of the pluses you have to do between terms into the minuses. So pretty much what you really have here is minus that amount. It is due to the order of operations. That's correct. Because remember, you do power before addition and subtraction. And then you're going to have -2 to the power 3. So what you really have here is -2, -4, -8. And you can see that this one is definitely not -6, correct? We actually get -14 out here. Now, an opposite question for such a problem might be, trying to find the opposite direction of what I have. So if I have, for example, 1 plus 2 plus 3 plus 10, how will I write that one using summation? So first of all, I need to decide how many terms I have. 10, correct? And then I start with the 1, correct? So since I start with I equal to 1, then I is going to be equal to 2, 3, and 4. So actually what I'm doing is I'm literally just doing a sum of I. Again, those are very simple examples, and you'll get a chance to practice some of them in a homework assignment. So again, I can play with powers, I can do many things. You generally need to figure out what is the property, like what is the connection between the elements. And in order to do it, this is where you look at every single element and try to find the sequence which is going to work out. And here is what I mean. So assume I'm going to have 3 plus 9 plus 27 plus 81 plus, and it's going to go into infinity. What I can do is I can say, okay, I'm going to have something here. What I need is I need to figure out what sequence am I having here? What is my iterative formula for my sequence? So the values I have are 3, 9, 27, 81. So what do? Yes, we multiply by 3 every time. So this is geometric sequence, correct? So now let's try and figure out what I have. So actually, if you think about it, I first have 3, and then I multiply 3 by 3, and then multiply 3 by 3. So I really have 3, and then 3 multiply 3, and then 3 multiply 3 multiply 3, correct? So what is my pattern here? Evan has already gave it away, so it's 3 to the power I, and my I is starting with 1. Again, is it always that easy? Of course not. There are actually summations which are extremely hard to figure out what is the property and so on. But this is why we learn the properties of sequences, trying to figure out what type of connections we study them, okay? Because sometimes we need to do those things. Okay, finally, theorem. If A and R are real numbers and R is not equal to 0, then the summation of AR to the power I goes from 0 to n is equal to AR n plus 1 minus A over R minus 1 if R is not 1, and if R is actually 1, then it is just going to be n plus 1 A. Now, actually, there are many other theorems of a similar ways for different algebraic expressions. This is geometric one. So there are really different formulas you can use for it. Now, in this case, if you have a formula of a form ARI, you should be able to calculate the summation pretty easy. And here is an example. If I want to evaluate something like 2 multiply 3 to the power I equal to 1 to 8, for example, one thing is I can definitely try and plug it in and actually calculate it. The other one is going to be to use the formula. In my case, R is 3. 3 is not 1, correct? R is like not 1. So I can use the top formula, and top formula is going to tell me it's going to be 2 multiply 3 to the power 8 plus 1 minus 2 over 2. I'm going to factor 2 on top. 3, 8 minus 1 over 2. I'm going to cancel the 2's. So it's going to be 3 to the power 9 minus 1, whatever the disaster is. And actually, you can kind of plug it really in and calculate it and compare if it's equal or not. So generally, there are tons of different theorems. Generally, you study them if you do mathematical classes. You study many of them in calculus 2, actually. They talk a lot about like conversions and inversions of series and different summations and so on. But this is just one example. But if you study properties and come up with those formulas, then evaluating things gets pretty easy if you know what formula to use. The last but not least is if you ever took programming, you know what if we talk about if-else statements, then we talk about if-else, 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 correct? So we're like doubling things up. If you have a for loop, then we go, what if we put one for loop inside another for loop? So even in programming, we like combining things together. So guess what? In mathematics, we also like combining things together. So what does it mean to have multiple sums combined? Okay, so where am I? Yes. So a summation of I equal 1 and another summation of j equal 1 is equal to I plus j. So for those of you who are computer science majors or took computer science programming, this is kind of really a for loop. One for loop inside another for loop and patterns, and you generally study it in Python and in Java and everywhere. So what you really do is you first figure out what's like you literally run it for every I and every J combination. And you need to be careful. So the way we're going to do is we're going to start with I equal to 1. And we are going to plug all possible values of J for it first. So it's going to be 1 plus 1, and then 1 plus 2, and then 1 plus 3, and then 1 plus 4. How did I get it? Well, I fixed I to be 1, and then I did this whole sum of J going from 1 to 4. So after I fixed I to be 1, I substituted all possible values of these. So this is kind of like my first portion. In the second portion, I did all possible combinations of J already for the I equal 1. Now I need to do all possible combinations for I equal 2. So this is going to be 2 plus 1, 2 plus 2, 2 plus 3, and 2 plus 4. And if you calculate this whole thing, you're supposed to get 32. So nested summations are going to work, do the fix one at a time every of the sums values, and then the most inner one, iterate on all possible opportunities, and then get to the next value and so on. Now, one more example is, assume I have a set S, and my set S has values 4, 5, and 6. What if I want to figure out a sum of elements of this set? So the notation for it is going to be the summation of S inside big S, S, like that. What this notation means is for every element inside the set added together. In this case, we do not have upper bound, because what we really say here is we are going over a set and we are picking one element at a time. So now what we have is 4 plus 5 plus 6, and it is going to be equal to 15. So for computer science people, this one is kind of like in Python, you have a thing for I in list, correct? And this is a summation. So this summation of all the things. Now, this little sign, this is why I said it is important to remember everything we study in this class. This is S belongs to S. Remember this sign out here, this means belong, correct? So for every S and S. So yes, now in here it's going to be sum equal to 0, and in here it's going to be sum equal to sum plus I. That is going to be like programming alternative of those summations. But in order to understand what's going on, you really need to understand the math behind it too, correct? Okay. And this one was more of a for I in range. And then you play with the range of functions if you're in Python. If you are in Java, things are a bit more complicated. Okay. So section 2.4. Homework assignment. 2, 6B, 10, C and E, 12D, 14, 16D and F, 18, 26 B and H, 30 A and C, 32 B and C, and 34 B. Lots of problems to practice. Again, remember this section was pretty long because we first talked about sequences and iterative formulas of recurrence formulas, and then we talked about summation. So this section actually has a lot and a lot of information. Okay, so now let's talk about section 2.5. And again, the homework assignment is going to be on icon after the class. So countable versus uncountable sets. Okay. So who can remind us what is the cardinality of set? Cardinality of set. Yes, David, number of elements. Good. Okay, great. So A and B have same cardinality even only if there is one by Y correspondence, which is bijection, from A to B. This is kind of really interesting because what it really says, if I have a set A and I have a set B, to have the same number of elements mean I should be able to map all the elements of A into elements of B in a such way that no two elements end up in the same element. Moreover, all of the elements of B are going to have a pre-image, and there is going to be an inverse function. So yes, bijection also requires to be one-to-one. But remember, we said it is a bit confusing, but there is a difference between one-to-one function and one-to-one correspondence. One-to-one correspondence is equivalent of bijection. So in here, I'm not saying it is one-to-one function. I'm saying it is a bijection. So those two are same terms. One-to-one correspondence and bijection means the same. And one-to-one correspondence, it's not the same as one-to-one function. Okay? And this is why I said I always going to also write bijection for you and try to use word bijection because it makes more sense. So you can kind of do the mapping. It doesn't mean in a unique way. Actually, there is more than one way, but I will have to cover all elements of B, and I cannot send two elements of A into another element. Then it's going to say that cardinality of A is the same as cardinality of B. Now, next time we will start by watching a cool cartoon about infinite cardinality and infinite functions. I hope you'll enjoy it. I'll try to set it up so you can hear the video. On that note, we are done today. Don't forget to submit your homework, and I'm going to change properties of the quiz. It's not going to be timed anymore, and you will see the question, and it's going to cost 0 points. Okay? Have a good day and great weekend.